Okay, it would be good if you turn your video on, because here in the room there is nobody. And so, yeah, because if I don't see your faces and I forget to say something important, then I know faster about it. Okay, so the topic of this lecture will be so the main goal of this lecture is kind of a nice formula. Uh, so before we spoke, so the goal is to derive a risk bound in a new risk bound, not based on VC dimension, but so VC the risk bound is essentially based on growth function from previous lecture, and now we will use a better technique. So growth function is based on counting dichotomies of hypothesis class on a set. Rademacher complexity. So we will speak about Rademacher complexity. Is a different way to measure complexity of a class for a given size of the training set. And it measures, oh, thank you. It measures random correlation with so it measures correlation with random noise. So we say that the class is very rich if you can correlate well with random noise. So we will use random -1 +1 variables, and our main result is quite almost a really nice statement. And so it says that expected error. So the expected risk of our classifier on some measure P. Sorry, there is no. So the risk of our classifier. So just for every classifier in certain hypothesis class, we know that error on test set is bounded by empirical error, so the error on the training set, plus this Rademacher complexity for the distribution of the class, plus some small fluctuation that we get from Chernow bound style. So this is ln1 over delta divided by 2 of n. So the main goal of this lecture is to prove this statement. And so what happens is if we generate the usual thing we have in the risk bound. So here S is a training set which we randomly generate n samples using measure P over input and output pairs. And then we say that for every F in the class, so if we want to measure, yes, please comment. So for every F in the class, this risk bound is valid. So in other words, our measure of correlation with random labels precisely gives us the difference between error in training set and test set, and up to some statistical fluctuation from Chernow bound, but we know this very small. And so usually delta is whatever. So people are happy to set it to like 1/4, but even if you set it to 1%, after you divide by the training set, nothing is left. So this is nothing, and so this is our nice term. But unfortunately, Chernow bound is not powerful enough to prove this inequality, or Hoeffding bound. So we need something slightly stronger here. It's called bounded difference inequality. And so we will first speak a little bit about this one, because we also had some unproven inequality that we used in the proof of previous lecture on VC dimension. So I think the homework deadline was today. So you're now specialist in this proof on how get the risk bound from VC dimension. But there we used this bag with objects, and that it also satisfies Chernow bound. So if you take random half of, okay, I will just say that in a minute. So we will prove this bounded difference inequality. Well, I will just state it. So the proof is another homework task because it's completely the same as proof of Chernow-Hövding bound. And so this bounded difference theorem considers a function phi, and it has n arguments, so they can be from different spaces, and it maps to real numbers. And the claim is that if we generate the arguments independently, then phi will be close to its expected value. There is one condition: phi should not depend too much on the individual argument. So if we keep all arguments the same, but we change one of the arguments, then f should change only a little bit. So under this condition, we have that phi is equal to its expected value up to epsilon with the same bound from Chernow bound. So let me say it completely. So so take a function phi, and now we assume, so if we fix a training set for all x1, how should I say it? Okay, for all let's take a tuple x1 in x1 times xn. So we also take for all I smaller than, so we will change one element and require that the difference is bounded. So let us have some tilde xi and also in xi. We require that phi of x1 till xn xi minus phi of x1 xi tilde xn is bounded by some different b. So then the random variable, so I will use capital phi equals to phi x1 till xn with xi independent. And so now we have the Chernow bound. So probability that phi is bigger than expected value of psi. Okay. Plus epsilon times n is smaller than exponent minus 2n epsilon squared. And so here the bound that we always use in computer science, I mean at least for indiscrete math. So here is the result. And so Chernow bound follows if we use this function phi to be just the sum of the variables. Then we have back the Chernow bound. So this is a really cool result because you can use it to any function phi. So there exists a generalization of this. I forgot the name with martingales. Let me see how it's called. But it's hard to state, so I need more definitions. Okay, I wrote. Okay, so what I'm saying is that actually this condition of xi's being independent, it's not really needed. So what you just need is that this function is martingale if you iterate over next variables. But okay, then you need to know what is martingale and so on. There's many conditions. So this generalization is a bit hard to state, but it's also useful if you want to do real research. But with this is enough for our course. And so proof is the same as I said as Chernow-Hövding bound. I mean, almost the same. So, but let us speak about some examples. So it's clear, right? This, by the way, is the marker good enough? You can, yes, I think so. Okay, so let's do some examples from computer science. So there exists a bin packing problem in operation research. So here you are given a bunch of numbers, x1 till xn, so numbers between 0 and 1. And you need to pack them inside bin of size 1. So for example, if you get the number 1/8, 1/4, 1/3, 1/2, and 1/5, for example. So the question is, what is minimal number of bins to store items of this size? And again, bins have size at most 1. So for example, we can take 1/8, 1/4, and 1/2 together. So this is one big, and here, so here the answer is, so phi x1 till xn is equal to 2. Sorry, yeah. So here, in this example, is equal to 2. And so because here we have big bin 1, 1, and 2. Okay, and so this is famous NP-complete problem. So given a set of rational numbers, find the minimal number of bins. And the cool thing is that this problem satisfies condition of bounded difference inequality with b equal to 1. And so it's clear, right? So the input, so if we generate the bins independently, then the optimal number of bins will be very close to its expected value. And so why is the reason? So condition is satisfied. If we change the size of one bin, then the answer phi of one object, then we can have at most one bin more or less. And so if we increase or decrease, so xi tilde, and so if we take one object and then choose a new size for this object, then we need at most, so then this will be either at most one more or at most one less. So this is valid for b equal 1. And so the result is that probability that number of bins is more than expected number of bins goes down very rapidly. And so you can choose epsilon by 1 over square root n to get something here that is reasonably small. Okay. So another example is in bioinformatics. And so there is two sequence of proteins, and you want to find longest common subsequence. So you want to find the maximum number of positions where the it's not so you want to insert and delete. So here is a list of amino acids, and you want to like for one sequence, so you want to delete amino acids from both sequences so that they become equal. Okay. Somebody asks something. Okay, so what is longest common subsequence problem? So there are symbols from some alphabet to sequences. And the question is, what is minimal number of symbols to delete in both sequences so that they become equal? So longest common subsequence problem. And so if symbols are generated independently, then this problem can be solved by dynamic programming. So it's special case of edit distance with certain operations, like deletion and insertion. And here again, if elements are generated independently, we know that the length of least common subsequence is satisfies such a relation, is close. So this length is close to its expected value. And there is like, even if you have binary alphabet and generate symbols independently, then it's open question, what is the expected value of this longest common subsequence? There seems to be some value square root related to square root 2 that's experimentally observed. But as far as I know, there is no proof. At least last year, some student told me there exists some result, but I forgot what he told me. I already getting on. Okay, so this is enough about bounded difference inequality. Now we understand how to apply it. We will also use another inequality which we can prove. So so the proof follows from Hoeffding bound. So the other inequality we will use is called maximal inequality. And here we have a matrix of random variables so that rows are independent. And we want to bound the maximal sum of, columns are independent, and we want maximal sum of a row. So we want the bound of this. So let me write all the conditions. So we have xij such that, so I keep forgetting it. So columns are independent. So we have xi1 till xin are independent. We also know that these variables xij, they are in a certain bound. They lie. So their values depend on the columns. So there are some rj's, numbers rj. We also assume they're centered. Xij is equal to 0. And then we are interested, in the maximum of sum of rows. Vi is equal to R1 x I1 plus Rn x In. And so now the claim is that the maximum of the VI's is bounded by, and so the norm, the 2 norm of the R vector times 2 ln, well, I need the size of the matrix. So the number of rows is d. And then we have here norm of R square root ln d. So let me double check that I know this is notes in chapter 10. But I forgot to explain how we use the maximum difference inequality to get the result with the backward marked objects. So it's not so easy. Yeah, so okay. Now my structure of the lecture. Okay, what I wrote is correct. Yes. Okay, so for backward marked objects, we don't need it in this lecture, so I propose you just read it, because otherwise, if I skip too much, we're wasting too much time. Okay, so let us prove a theorem here. Here I smaller than. And the proof is also kind of nice. So the plan is to bound this maximum using softmax value. So we will choose later, we will choose some S at least 0, and then we will use that the maximum of VI is bounded by the logarithm 1 over S, logarithm of the sum over exponent S. So here we go, I smaller than V. As VI. So it's actually a method to bound maximum in continuous way. It's used in many places in machine learning. So it's just so the proof in itself. So you can remember, you try to remember this. Okay, and so now what we have to do. Oh, sorry, I forgot to write expected value. This is kind of like intuitive result. So expected value of the maximum is bounded by this thing. And it's kind of what we expect from Chernoff bounds or Hoeffding inequality. So just think that usually all the R's are equal to 1. And so what we have here is 2n, the square root of 2n ln d. And so this is just if we like, so here we have expected value, but it's kind of what we expect from such a thing. We expect probability of deviating. And so remember, columns are independent, so we are summing many independent values, and we know that large deviations. So deviations more than square root of n, they are rare. And so we assume that it's easy to believe that if we take these such experiments, then by union bound deviations will so we want to insert some delta. So we want to use this result, and we want to get it from some delta smaller than 1 over d to then apply the union bound. And so then if we solve 1 over d for this thing, we find some epsilon equal to this thing up to constant factor. So this is a very natural bound. But the proof is kind of funny. So from Hoeffding bound. Okay, so what's our plan? We will take expected value here from the maximum. And then by the way, before I take the expected value, is it clear why this inequality holds? So let us see. I forgot myself. So okay, it's clear if there is no sum, it's easy, right? If we forget, if we fix I and forget about the sum, then this says that okay, so we take the I for which this is maximal, and then we fix this term here, and then the logarithm, the x, and the s and 1 over s cancel. So this is clear. So in the morning, it is hard to understand for me, but okay. So now our plan is to take expected value, and so we take expected value on both sides. And we know ln is concave, so we can use the Jensen inequality. So let us look to so the logarithm we can put inside. So the expected value we can put inside the logarithm and have some expected value here. So let us look at one term. Expected value, exponent s of VI. But VI we can expand by the definition. It's a sum of many random variables. So, okay, let me write it. FSI, it is exactly equal to product over I smaller than D of expected value of exponent. So note that columns are independent, so I can flip product and expected value. But okay, it's not really, this step is not really needed. Product, I have J smaller than N. Okay, and now we apply Hoeffding bound. So know that expected value of Xij is equal to 0. But I want to take expected value of an exponent. So we cannot apply Jensen inequality, we need Hoeffding bound. And then we know we have this bound with 1 over 8. So this is bounded by 1 over 8 s squared. If x is a variable between 0 and 1. Okay, but that's for non-centered value. So if Xij is inside unit interval. But here our interval is 2 times Rj. So we have to rescale S by 2 times Rj squared. So the factor is 1/8 times 4 Rj squared. So we don't have expo. So in the version we've seen before, we had S squared divided by 8. Right? But now we need to scale. So we will need to multiply by 4 Rj squared. So we have that this is bounded by expected value of exponent minus 1/2 Rj squared. And I forgot the product is still here over all I smaller than N. Okay, and sorry, it is J smaller than 10. Okay, and so when we take the product inside exponent, it becomes a sum, and so we have here this is equal to exponent R squared over 2 with the minus. Okay. So this is for one single term, and we see that expected value does not depend on I. It does not depend on the row. So this is explanation to say that the top one is bounded by 1 over S ln of D times, so ln of D plus, so note that we have logarithm and exponent that cancel each other. So we have ln D minus R squared over 2. And so there is a minus, it's a problem. Yeah, and of course in Hoeffding bound, we don't have a minus here. We have a plus, so. Okay. And I forgot about the S here. So there is also a factor S. Sorry, I need to incalculate. So there is S squared here in the. So I forgot also the S squared. We have an S squared here. Okay, and so now we have a term that is proportional to 1 over S, and here a term so that's proportional to S. And so the optimal value is obtained for S equal to And it's the typical square rooting. So such formulas we have a lot. Equal to ln over 2r. 2 normal r. And then when we insert this s, so this is optimal value. When we insert it, we have this bound here. Okay, so this is nice proof for maximal inequality. And then in the seminar, you will have some applications of it. Okay, so this is all the preparatory materials on measure concentration. And so now we can go back to our main result for this lecture. So it's the last main theoretical block before we go to applications. And so this is also the last result that holds for all distributions P. I mean, the risk bound that's interesting for, that's possibly interesting for all distributions B. Okay. So now we are at chapter 11. And the first thing I have to do is explain what is this Rademacher complexity. And I already told it is correlation of best classifier in H with a list of random labels. So let me first make some space and then write the definition. Okay, and unfortunately, I will need more space. I will need to delete this part too. But okay, let's first start with just writing down definition. And we start not with average empirical Rademacher, average Rademacher complexity, but we will start with empirical Rademacher complexity. And so let's just say what it is. So we will generate random labels. So we will take an expected value over random labels. So -1 and +1. And given a training set, so the empirical Rademacher complexity depends on training set. And so this result, this notion will also be needed for to discuss regression problems. So in this course, I don't want to talk about regression, but I will be forced to talk about it. So I will speak about, okay, I need to make some choices. So I decided to only speak about classification, but then do it like in more depth. But so that means that we will speak about functions with real values now. And also I will kind of join training set and inputs and outputs, X and Y. I will join them somehow. So I will use a training set I will represent by a set Z. So it will be equal to Z1 till Zn. So at this moment, everything is very abstract. And so in this lecture, it will remain abstract. The next lecture, we will speak about support vector machines. And hopefully at the end of next lecture, things are clear. But for now, so the training set, so there are input-output pairs. I write them for the Z1 till Zn. And also, we will consider a function from Z to real numbers. Okay, and so now I say it is correlation with random labels. The random labels will be called sigma 1 till sigma n, and they are from -1 till from their -1 or +1. And so we start with writing down correlation with a function sigma n f of Cn. Correlation has, and we normalize like this. So now we assume that sigma 1 are random labels. So we take S1 uniformly from -1 plus 1 in hypercube. And so every sigma 1 is equal to sigma I is equal to -1 or +1 with probability 1/2. Okay, by the way, there are many students online now. So please, can you switch on camera? Because otherwise I don't know if I'm saying something clear. And if I don't see your faces, I will, yeah, thank you very much. Yeah, it helps me to stay focused. If I see, if I try, yeah, if I get distracted and I say something stupid, I immediately see your faces and I correct. But without the feedback, it's dangerous. Okay, so here we have average correlation, but we will use a best classifier in M. So not of a set F of functions from Z to R. So here we will use a whole set of regression functions. So F is whole set of regression functions, and we look to the best classifier in F. So it's average correlation. So average correlation of best classifier. That's the definition. So this is equal to empirical Rademacher complexity of the set Z of the class F. Okay. So let's check a few things. So imagine that the set F contains only one function. So then what do you think is this empirical Rademacher complexity? So it's denoted with a head. Hard head C. So what will value be? Imagine there is only one function f here. So we don't need to write the supremum. So we can think supremum is not here. And so then we have expected value over 1 over n sigma 1 f c1 plus sigma n f cn. Okay. So note the sigma i's, they are independent because we take a random point from hypercube. All right, so before each point is independent. So fz1 is constant because here we just fix the training set. So what is this equal to? It is 1 over n fz1 expected value of sigma 1. And then plus for the other terms. So now, what is this value?
0.
Yeah, exactly. So all the terms will be 0, and so the sum is 0. So if there is one function, empirical Rademacher complexity is 0. So its smallest function. Okay. So second property. Imagine that we have imagine that we take a set. We have another set of functions g that is larger than g. So what can we say about Rademacher complexity of g compared to Rademacher complexity of set f?
It is not less than the Rademacher complexity of the set F.
Yeah, exactly. Indeed. Okay, now imagine that H is a set of classifiers with values -1 plus 1. So H contains functions, is a subset of -1 plus 1. So mappings from X to binary labels, -1 plus 1. So can you give upper bound on empirical Rademacher complexity of H for any non-empty Z or even empty Z? Oh yeah, let's say non-empty Z. So what do you think? Okay, I make it easier. Let us say that H is equal to the set of all binary classifiers with values -1 and +1. So what will be this Rademacher complexity? So we have all classifiers. Okay, and let's assume that all elements in Z are different. Okay, so all elements in Z are different, and H is the class of all, and H is a class of all binary classifiers. So what will we have for empirical Rademacher complexity? Okay, it seems to be harder question.
0.
Ah,
0 or not?
no, not 0. So it's kind of like the class with highest possible complexity. So remember, what is our aim here? So here we want to bound with, this is average Rademacher complexity. We don't know what it says, but we don't want to have Z here when H is a class of all, set of all classifiers.
Oh. 1, excuse me, 1.
Yeah, that's it. Yeah, 1, exactly. So it is equal to 1, and that's kind of perfect for the risk bound. And why is it 1? Well, when all points are different and we can choose all the functions, then we can choose function equal to the random labels here. And so we have 1 times 1 plus 1 times 1 and so on, n times. So we have here n divided by n. So the best function will be equal to the random labels. And so in this case, Rademacher complexity is maximal. But here we use values bounded with the absolute value by 1. But if class has much fewer functions, then we have better bound. And so we can get bound of Rademacher complexity from, so if class is finite, so if we have finite subset, then maximum inequality gives bound on Rademacher complexity. So why is it? So from maximum inequality, we need matrix. So columns are independent and we sum rows. And so here you see sum of row. But what are the rows? They are the different F in finite class. So when we apply for H being a subset of classifiers, then we can create a matrix here. So we can write it for all the classifiers, and then we take the maximum. So then we have maximum of sum of rows. And so well, in this case, if function F is bounded by -1 plus 1, we and also labels are bounded by +1. We have symmetric random variables. And so just think of all of the matrix. Okay, I need to make some space anyway. So so if H is finite and H is subset of -1x, then we view the matrix as sigma 1, F1 in Z1, and so on, sigma 1, F1 in Zn. And then we do the same until we have sigma 1, F size of H here, V1 plus sigma n. Well, here should be sigma n, and here we have sigma n. Okay, it's clear. So we just have a matrix with random variables, and all of the random variables, they are bounded by absolute value in 1, and they are symmetric. So it's precisely what we get from maximal inequality. And so we know that this supremum in this case, so if H is in a subset of this thing, we have that Rademacher complexity is bounded by this square root. So we have 2n L n D. So norm of the R's is square root of n, because all R's are equal to 1. And okay, so this is nice bound. But I should speak about more properties, simple properties. So there are basic properties. I did A, B. Okay. First of all, Rademacher complexity is always non-negative. So for any f, our z of f is at least 0. So why is it true? Sorry, of h. Yeah, I kind of wrote the answer.
Because we can select a function from f and say that the Rademacher complexity of the whole set is greater than the Rademacher complexity of this function, but the Rademacher complexity of this function is exactly 0.
Yeah, exactly. So when I write f and g, I will always assume that they are non-empty sets. And the same for h, like we did before. I'm not going to repeat it all the time. And so then we have this result. When we say f is non-zero, we know it contains one function. So just pick one function, then we know the Rademacher complex of this is 0. And then if we add more function, it can only increase. So by the first two properties. Yeah, very good. Okay, so then D, I kind of, okay. So let's go back to binary classifiers. We also have that Rademacher complexity of a set of binary classifiers as 1 if and only if the set shatters Z. So we have that RH is equal to 1. So know that for binary classifiers, 1 is the maximum if and only if H shatters Z. So why is this true? Well, it's extension. So we prove that if H contains all classifiers on Z, then it's equal to 1. But the opposite is also true. If 1 is missing, then we cannot have, for the missing value of sigma, we cannot have the corresponding function, and the correlation must be strictly less than 1. So it's in both directions. Okay. So this is property D. Then property E. So that there is a list in the notes with a huge number of properties, but all easy ones. So what if we consider the class for some space? So as usual, F is a class of this form. And now let's define the class F plus A. A is a real constant here. And so it's equal to all the functions of the form X, they go to, or sorry, better write Z, F of C plus A for all F and F. So just the functions you get by adding a constant. Rademacher complexity of, what do you think is the Rademacher complexity of F plus A? So what do you get here? So just we add the same constant to all of the functions. So we do a constant shift. Okay, so think about the case there is one function here. And so what happens if we add a constant to all of these functions? Then we can take this constant in front of the expectation, but sigma 1 also appears in the front. So it will be equal to Rademacher complexity of M. And because expected, so again, let's look at so we have supremum of 1 over n sigma 1 f1 of f of c1 plus a, like this. Okay, so this plus a we can take out of the supremum. We just add a constant, we can take it out. But also sigma 1 comes out of the supremum. So we can just get rid of the a and then write plus expected value of sigma 1 times a. And so this is equal to 0. Because of symmetry of Rademacher variables. They are -1 and +1 with probability 1/2. Okay, so we can add a constant to all of the functions a here, and it doesn't change. So there are a lot of nice linearity properties of Rademacher complexity. So now let's change the definition. Let's see what happens when we multiply all functions with the constant a. And so let's assume a is non-negative. So here we apply with a for all f. So what is Rademacher complexity of a times f? Here, this one is easier.
A times original Rademacher complexity.
Yeah. And now let us try the same question for a minus 1. And so here I assume a at least 0, but what happens when I look to Rademacher complexity of minus f? What will it be?
It's same.
Yeah, exactly. It's the same. And because why is it the same? Here, look at the expression. So the sigmas, they are symmetric variables. This is very important point. It's main observation from the proof that we will need here. Very important. Sigma variables are symmetric. So if we replace f by minus f, that is just the same as flipping all the signs of sigma, but they have the same distribution. There's sigma and minus sigma have the same distribution. So we can just replace minus sigma always by sigma. Okay. So now let us take the product of f and a function h. So here we let h be don't need this anymore. So h is a function from z to -1 plus 1. And so now let us define h of z, f of z of f. So now we let the sign depend on the z's. And the question is, what is Rademacher complexity of h of f? Here. And equality holds for precisely the same reason. And so here, what happens is, in front of every f, we put a sign that depends on the z. So here in the formula, we insert a function h. So we will have h of z1 and h of zn. But each Rademacher variable is symmetric. So we can replace it by minus z in case h of z1 is -1. So nothing changes. So here we can change the signs of the Rademacher complex. Okay. And so a nice result is that both for +1 and -1, for positive and negative numbers, A of f equals to absolute value of A. And why is this very important? For many reasons. But for example, in neural networks, we build classifiers from more complex classifiers. And the first thing we do is take linear combination of previous neurons. And oh, sorry, I forgot to speak about some. Okay, but the cool thing about Rademacher complexity is that it's basically a linear mapping. So it preserves linearity. It has linear properties. So let us now define. So we have two classes of real functions, f and g, and we define the sum of them of all functions that are sums from f and g. So f of z plus g of z, or all f and f and g and set g. So now the question is, what is Rademacher complexity of f plus g? So the claim is that this is Rademacher complexity of the sum. Sum of Rademacher. So Rademacher complexity of sum is sum of Rademacher complexity. Okay. So why is it true? Okay, now we let's look to Rademacher complexity here. So we have expected value of S over sigma, and we take supremum over two functions. We take supremum of over f plus g. So that means that we, since they are defined independently, we can take, when we take supremum over f plus g, we can take separately supremum of f and over g separately. And then we have 1 over n, the sum over sigma 1, f1 of z1 plus g1. Sorry, there is no index. G of z1 plus sigma n of f of n plus g. Okay. So, but now it's clear, right? We take supremum over either f and g. But each first term only depends on f, and each other term only depends on g. So this follows, right? Because we can write supremum over pair as sum over two supremums. And so all these first terms only depend on f, so we can collect them in the first supremum. And this supremum no longer depends on g, so we can drop it. And then we can collect all the g terms in the other supremum. Okay, so it's boring for some people, but it's because too easy or too difficult. So you need to say something if there is problem. Okay, so next, so here, what if we can? So if there is general property now, if we have a large number of sets, and we take arbitrary linear combination, so we have that Rademacher complexity of A1 F1 plus AK Fk of C, empirical Rademacher complexity. is equal to a one absolute value of Rademacher complexity of F1 plus AK Rademacher complexity of Z of. And so we can take arbitrarily linear combinations, and this will be very important property. Okay, next thing that we need, let me double check what we need. So G we did, H we did, I yes, lemma 1.13, that goes very well. Okay, and then the last important property is convex combinations of F. So this one we will need for boosting. So boost, when we do other boost, we will compute convex combination of a set of base classifiers. And here a magical thing is, so Rademacher complexity of convex combinations of classifiers in F is equal to Rademacher complexity of F. Okay, so what is convex combinations of F? So I think you can guess it. So convex of F is equal to, okay, let me define it. Convex combinations of two functions in F is just equal to the set of alpha F plus, okay, let me write it in detail. Z goes to Z goes to alpha F of the Z plus 1 minus alpha G of the Z. And then alpha is from 0 to 1, F in F, and G also in F. Okay, I'm afraid the marker is not so good anymore. Let me see. I have another one. So should I rewrite this? It's clear? Can you read it? No. Okay. So let me start. So let's write everything. When Z goes to alpha times F of Z plus 1 minus alpha G of Z. And so we have alpha is number between 0 and 1. F is in F, and G also in F. Okay, now it's better, right? So just convex combination of functions, you multiply the first function by alpha, second function by 1 minus alpha. And so in general, there is no 2. And so you can take any finite sequence of functions and multiply them by coefficients that sum up to 1. So, but let's just note that just inductive application of conv2 operation gives you the general convex operation. And so let us prove that convexity of F is equal to this. So why is it true? And that is proof. And the proof is very similar as for the sum. So we are interested in expected value. Well, actually, let's not write the expected value and just fix any sigma. And let's look at the supremum for F in conv2 of F. So let us take supremo. So what are these functions? Well, instead we can instead of taking a single function, let's apply the definition under the supremo. So we will take supremo over f in g and alpha in 0, 1, and then look to 1 over n times correlation. So we have sigma 1 times alpha f of C1 plus 1 minus alpha G times Z1 and the same thing here. Okay. Alpha f plus. Okay, and now we have a block of terms that only depend on f and only depend on g. So we can write this as the same supremum over all these things. 1 over n, and then something that depends on f. Let me call it psi of f plus psi of g. All right. And here we have the supremum over f and g and f, alpha in 0, 1. I'm sorry, we have alpha, and all these other terms are of the form 1 minus alpha. And so what will be the best value of alpha? Best value of alpha will be 1 if psi is larger than psi, and 0 otherwise. Right? So we can just replace alpha, so we can drop just alpha here. So we can say alpha equal to 1. We can fix alpha equal to 1 here, because either we have the best expression for f, or we have the best expression for g. But we also take supremum over f and g. So this is just equal to, yeah, so actually we have 2 times the same expression. Psi. So that's what we have. So psi equal to psi of f is equal to sigma 1 f of c1 plus sigma n f of cn. Right? So we have 2 times the same expression for f and g. And so when we take supremum over alpha, we can just drop it, and this is just equal to supremum over f and f of 1 over n psi of f. Right, so it's just original Rademacher complexity. Okay, this is cool result. So when we take convex combinations of functions, Rademacher complexity remains the same. And this is what Adabu is doing. It computes convex combination of functions. And there people see we take a huge number of functions and take their complex combination. Why overfitting does not happen if you're fitting linear combinations of functions? And this is explanation here, the technical explanation. It is because we can bound error on test set using Rademacher complexity, and it doesn't increase error on test. So this is from 23 years ago. So if machine learning teacher says that statistical learning theory is wrong because more parameters is better, he is behind at least 23 years. So, okay. So this is last important property. And now last task of this lecture. Wait, how much time do I have? 10 minutes. That's not so good. And there is quiz. Okay, but let's speak 5 minutes about proof. So this is corollary of, so this is a theorem for classifiers. H H is set of classifiers. So we need a theorem in next lectures on real functions. And so let me write down the theorem. So here we use so here we will use a set G, and it has values between 0 and 1. So we map some inputs from Z to 0 and 1. So we use bounded functions. And we bound the difference between expected value. So we will say that we will generate a set Z, a training set for Z taken from Pn. So we generate n elements of Pn, and then we estimate expected value. So we will have for all functions G and G, expected value of G is bounded by empirical estimate of expected value, sum I equal 1 till n of G is I, plus 2 times Rademacher complexity of the class G, plus, and then the typical square root fluctuation term, ln 1 over delta divided by 2n. So this is most important result. Okay, and then here goes the proof. Before proof, we will use triangle inequality for supremums.
Can I ask a question? What does the segment from 0 to 1 in the degree S mean?
Sorry.
In the condition of the theorem?
So,
The G being
so functions from Z, so G contains functions. G contains so in other words, all the functions are non-negative and bounded by 1.
Thanks.
Yeah. Okay. So this will be corollary from this theorem. I mean, you need to think a little bit, because here we will have functions with labels -1 and +1. So, and we need to have 0, 1 loss. We need to apply to go from expected value here to risk. And so here we take a Z from P, and here, yeah. So to say, yeah, okay, it's so yeah, okay. So so let me briefly say for the proof, and we need one technical thing about supremums. So we have supremum f minus supremum df is smaller than supremum. So this is clear, we will use it. And so now let's go to the proof. And let us look to the maximal difference between this and this. So let us make a function phi. Phi of Z, the training set. And this is equal to supremum for G and G of 1 over n, sum of GZ. Oh no, we need the other side. We want to bound expected value for z from P of GZ minus 1 over n sum over GZ. Okay. So yes, first we prove, and I will multiply this by n. So there will be an n here and no normalization here. And so now we should remember about bounded difference inequality. So first we will apply bounded difference inequality to bound statistical fluctuations here. And the first thing we have to do is understand what happens when we, so here is a list of variables. So here phi is a training set. It's equal to Z1 till Zn. Right? What happens if we change one of the Z's? I claim that phi changes by at most 1. So why is it? So where are the G's used? They're only used here. And so since all the values of G are bounded by 1, changing one term in the sum will lead to a change of at most 1. So they're inside the supremum. But if we take supremum over a vector or a function, but we change all the values by at most 1, then the supremum can also change by at most 1. So this satisfies bounded difference inequality. And what we see is that we now know that a phi, so probability over Z from P. Oh, there is one thing I didn't say here. It is average Rademacher complexity, not empirical Rademacher complexity. That means that I need to write definition. It means that it's expected value for random training set. So Rademacher complexity of P of the set F is equal to expected value for Z from Pn of empirical Rademacher complexity of Z of F. This is of course important. Okay. Well, this is average Rademacher complexity. And by default, Rademacher complexity, people means average Rademacher complexity. Okay. So we have this, everything we said for empirical Rademacher complexity holds for average Rademacher complexity. There is just extra expected value in the definition, but all the proofs, everything is the same. So what we now know is that if we take a random variable, probability that it's bigger than expected value of psi plus square root ln 1 over delta divided by 2n is smaller than delta. And here we have with probability 1 minus delta. So here we have bounded difference inequality. Now the only thing that we need to do is prove that this is bigger. That expected value is smaller, is bounded by 2 times the Rademacher complexity, the average Rademacher complexity. So this is our remaining work. We have expected value of psi is smaller than 2 times Rademacher complexity P of F. So this is only remaining work. This is the bound we have to prove. And I will tell it next lecture why it's true. Because it is already end of lecture. So I prepared quiz since everyone is on Zoom. I even have grader. So you can solve quiz now. Wait, let me share. Cannot share screen. Install. Seriously. Okay, let me put it on the wiki then. Wait, I will send you the link. First I copy on the wiki. Sorry, I need to get the link from Dropbox. Now I go to the chat. Oh, wait, let's put it in Telegram. Okay, so you all have Telegram. There is a link with quiz. And so you can open it and then read the questions. And try to answer them within 5 minutes. Oh, well, let's have more time. So till the end of the seminar, you can answer the questions. So you can email them. There is an email, right?
Till the end of the seminar, yeah?
Yeah.
Thanks.
Okay. So, and then you should get automatic reply with the grade. Yeah, question 4, I forgot the answer myself. So maybe, so we will, I will write something in the chat. Yeah, I will correct it now. Okay. So see you next time. Yes. Okay, this was last lecture with a lot of theory and no application. So next lecture is will be SVM. Bye.
Thank you. Goodbye.
Bye.